mathematics. How much gold can you hold in an elephant's ear? When it's noon on the moon, then what time is it here? If you could count for a year, would you get to infinity or somewhere in that vicinity? When you choose how much postage to use, when you know what's the chance it will snow, when you bet and you end up in debt. Oh, try as you may, you just can't get away from mathematics.
Good morning, grade 11s. Welcome to another physics class. Today's Thursday, April the 16th, and we're going to do pretty much what is the last part of this unit on electricity and magnetism. And yeah, we'll finish it up today and do some review over the next few days, and then next week you can expect to be writing a test on this unit. Before we get started today, I do want to encourage you again with a verse of the day. And so today's verse of the day comes from Galatians 2, verse 20, where it says, I have been crucified with Christ and no longer live, but Christ lives in me. The life I now live in the body, I live by faith in the Son of God who loved me and gave himself for me. I want to focus just on the last part of that verse. The life I now live, I live by faith in the Son of God who loved me and gave himself for me. So be encouraged by that. Live by faith in the Son of God. Live by faith in Jesus who loved you and who gave himself for you. And live out that faith actively, and encourage you to do that as you go through your day today. All right, yesterday we looked at the formula for the force on a current carrying conductor in a magnetic field. And today we want to parse it out a little bit and look at specifically now the force on a single charged particle. So current, what that is, current is electrons flowing through a conductor, right? And if we take out current, if we take one electron out of the current and we look at just one charged particle and we put it through a magnetic field, it will also experience a force. And so we're just gonna make it smaller, right? We're going to take the current carrying conductor, we're going to take one of those charged particles out and find the force on just one of the charged particles. And it doesn't have to be a charged particle in a conductor, right? Now it can be any charged particle. And we dealt with charged particles with fields and forces earlier, and with various charges. All right, so current is one kind of moving charge. There are other kinds of moving charge, and this formula we'll develop today will allow us to find the force on any charged particle. So a couple of things to remember first. Again, current is charge over time. So when we have current flowing through a wire, it's an amount of charge, a number of electrons flowing past a particular point in an amount of time. So current is simply charge divided by time. And we know from previous work that distance is velocity times time. So, and we'll get to this little box in a minute. F equals BIL. That was the formula we developed yesterday for the force on a current carrying conductor in a magnetic field. We had our magnetic field was B, current was I, the length of wire in the magnetic field was L. All right, if we take that apart and we look at just one charged particle, current is charge, that one charged particle passing a point in a particular amount of time. The length, well, the length of a wire that's in a magnetic field is equal to the distance that one charged particle would have to travel in the magnetic field. And we know that distance is velocity times time. If we make these substitutions, Q over T for I, V times T for L, we notice that the T's will cancel out, leaving us with B times Q times V. Now, that's the formula. I like to write it as F equals BVQ. And BVQ just rolls off the tongue nicer, it's a little easier to memorize, reminds me of barbecue, but it's BVQ. And so it doesn't matter which way you use the formula, it's all multiplication, order doesn't matter. Now I've added the sine theta to the end of it because, again, just like with BVL, or sorry, with BIL, there is a directional component to it. Again, most of our questions, all of our questions in the next little while will have the charged particle moving at right angles to the magnetic field, making sine of 91, which disappears. But if that angle is all of a sudden not 90 degrees, then we do have to multiply by sine theta. All right, now just a quick word about current versus electron flow. Current and electron flow go in opposite directions. So if I have a wire and I say the current in this wire is flowing in this direction to my left, that means that the electrons are actually going in the other direction. And again, this is a case of guys like Ørsted and Tesla and others who were developing formulas and developing the concepts around what current was, not having the technology to know what was actually going on inside the wire, right? They didn't know about electrons, they didn't know which way the electrons were going, but when they measured it, they measured current flowing in one direction. As technology got better and we were able to understand what electrons were more fully, they realized, oh, electrons are actually moving the other way. Doesn't change the formula in any way. Okay? In any of our formulas, when we get into units next year on electricity, it's not going to change the formulas in any way. But what it does do is it changes directions. And so with this, there's a directional component to it, right? And so we developed yesterday a right-hand rule for the force on a current-carrying conductor. And we said if we put our thumb in the direction of the current and our fingers in the direction of the magnetic field, the force was the direction our palm would push, right? So because current and electron flow is the opposite direction, what that means for a charged particle is that if we have a positively charged particle, the right-hand rule doesn't change, right? Because a positively charged particle would move opposite the direction of a negatively charged particle, if it were there, right? So when we have a positively charged particle, the right-hand rule stays the same. If we ever do a question where we have a negatively charged particle, or an electron is a negatively charged particle, then when we use our right-hand rule, we can still use the right-hand rule, but we have to realize that the force will be in the opposite direction because the direction is opposite of the electron, right? Our right-hand rule is for current, and it pushes. Electrons are moving in the other direction, so the force is in the other direction. So the force would be coming out of the back of our hand, right? You could, I'm not going to confuse you with this, but you could use the left-hand rule for electrons or for negatively charged particles because it automatically reverses the direction for you. It's still out of the palm, but it's now left hand instead of right hand. And in fact, if you ever go on to university and you come up with a professor, some professors choose to use left-hand rules. They choose to do everything in terms of the way electrons are moving. And so then all of our right-hand rules will be left-hand rules. And so that could happen. We'll continue to use right-hand rules. I'll always use right-hand rules in this class. But just know that could be a left-hand rule based on the way that the electrons are moving, not the way current is. We're going to do current. All right, hopefully that all makes sense. We're going to do an example on the other board. And again, hopefully it will make sense. So let's go do it. Here's our example. So in this example, we have a magnetic field, 0.25 Teslas pointing into the board. We have a proton, positively charged particle, moving so the proton has a charge of 1.6 times 10 to the negative 19 coulombs. That's the charge on all protons. It's also the charge on all electrons, right? Electrons and protons have the same charge, and that charge is 1.6 times 10 to the negative 19. It is a constant. Positively charged for protons, obviously, and negatively charged for electrons. But the number, the quantity is the same. 1.6 times 10 to the negative 19 coulombs. So that proton is moving with a velocity of 4 times 10 to the 6 meters per second to the right. What is the force on the proton? Okay, so again, force is a vector, so we're going to need magnitude and direction. Let's do the magnitude first. It's easier. Magnitude is F equals BVQ. Put in our 0.25 Teslas, put in our velocity of 4.0 times 10 to the 6, and our charge of 1.6 times 10 to the negative 19 coulombs. Put that into our calculator, nice and easy. 1.6 times 10 to the negative 13 newtons is the magnitude of the force acting on the proton. Now, direction. We have a magnetic field pointing into the board or into your paper. To diagram that, it's really hard to diagram it, but diagrams are really helpful with this. And you'll see some diagrams in textbooks and other questions that I'll give you in the next little while. when something is going into the board or into the paper, they will indicate that by drawing X's. Why X's, you might ask? Well, if you were to look at an arrow leaving you or going away from you, the back of the arrow might look like an X if you had 4 feathers on it, right? And so this is to indicate the back, the tail end of a arrow going away from you. Conversely, if we ever have a field or something moving towards us, they'll indicate that by just a dot, a point. And a point indicating the tip of the arrow coming at you. All right, so, and then they'll label it usually too, they'll say, be in. Okay, so magnetic field in. Okay, so that's the magnetic field. Now it says that a proton is moving with a velocity to the right. So I'm going to face the board here to my right. Here's my velocity vector moving to the right. There it is. And then the question says, what is the direction of the force? So let's take my right hand. Now we're going to use our right hand rule. Now the right hand rule yesterday was the thumb goes in the direction of the current. Well, that means now the thumb is going to go in the direction of the velocity vector. My magnetic field, which is my fingers, is going to go into the board. So that means my hand is going to go this way, right? Horizontally up. My fingers are going into the board. My thumb is pointing to the right. And since it's a proton, the direction of the force will be the direction my palm would push. My palm pushes in an upward direction, up the page, away from you. So however you want to indicate that, if it's going this way, would be our force. Okay, so magnetic field is in, velocity to the right, my palm pushes up. Now for you on your paper, you're going to be doing it vertically, so it's going to look something like this. You're going to have your hand going into the paper, your thumb pointing left, and your palm will push away from you. And again, when you're indicating it on your paper, I would like to you to use away from you, in, left, right. So you can go up, down would be, up would be out of the paper, in would be, down would be into the paper, and then away from you, towards you, or left or right on your directions. Again, when you write directions, your directions have to match what I'm looking at. So if it's on the paper, right here, it's this way, flat, in, out, away, towards, right, left. Okay, so make sure that you use these directions properly. The right hand rule, the direction is going to be the trickiest part. Remember to use your right hand. Sometimes you'll have to contort your right hand in a weird ways. Unfortunately, usually I get some entertainment out of watching students try to put their hands in the right directions as they do these questions. I will not get to see that this year, unfortunately. But I'm going to give you a few questions out of a textbook today, out of the other textbook today, handout. Just 3 questions today, for today. And then we'll start doing some review on electric and magnetic fields and forces over the next couple of days into next week, where we will eventually get to writing a test. As always, if you have any questions, email me and I'll be happy to go over them in a future video. And that's it for today. Hope you have a great day and we'll see you tomorrow.